There is a number that most people have never heard of, measured continuously by a small fleet of satellites orbiting roughly 700 kilometers above our heads. And over the past 2 decades, that number has climbed so much faster than anyone predicted that entire rooms full of climate. Scientists have started openly admitting they are not entirely sure why. The number is called Earth's Energy Imbalance, and in the simplest possible terms, it measures whether the planet is gaining more energy from the sun than it is losing back out into space, or the other way around. For most of the 20th century, that number sat close enough to zero that scientists could treat Earth's climate as being in a rough, stable balance. Today, it does not. Today, that number has climbed to a level that satellite instruments were not originally expecting to see for decades, and the scientists responsible for tracking it have used words like alarming, surprising, and taken by surprise to describe what their own instruments are showing them. This is not a story about a single freak weather event or one unusual season. It is a story about the fundamental accounting system underlying every climate model currently in use, and about what happens when that accounting system starts producing numbers those very models did not predict. By the end of this video, you are going to understand exactly what Earth's energy imbalance actually is, how scientists measure something this abstract with genuine precision, why the reading has become such a serious point of concern within the research community, and what a room full of 44 climate scientists meeting at a castle in Germany earlier this year actually concluded when they sat down specifically to figure out what is going on. If the idea that scientists are quietly recalibrating their understanding of the climate system based on a single measurement genuinely surprises you, drop a comment and let me know. And if you want to keep following stories where the real science behind a headline turns out to be more interesting than the headline itself, go ahead and subscribe now, because this particular puzzle is still very much unresolved. Let's start with the basic physics, because once you understand how this number is built, everything else about why it matters becomes much easier to follow. Earth constantly receives a massive stream of solar radiation, averaging somewhere around 340 watts of energy per square meter across the entire planet. Some of that incoming energy gets reflected straight back out into space by clouds, by ice, by snow, and by other bright surfaces, a property scientists refer to as albedo. Whatever energy is not reflected gets absorbed by the atmosphere, the oceans, and the land, warming the planet in the process. And Earth then radiates a portion of that absorbed energy back out into space as thermal infrared radiation, essentially heat glowing outward invisibly from every surface on the planet. When the amount of energy Earth absorbs and the amount it radiates back out are roughly equal, the planet's average temperature stays relatively stable over time. When more energy comes in than goes back out, even by a small amount, that surplus energy has to go somewhere, and it accumulates within the climate system, primarily by heating the oceans, melting ice, and gradually raising the temperature of the atmosphere and the land surface. That surplus, the gap between energy absorbed and energy radiated away, is exactly what Earth's energy imbalance measures. And it is essentially the single most direct physical signature of whether the planet is actively warming and by roughly how much. Measuring this imbalance with any real precision sounds almost impossibly difficult when you think about the scale involved. And for a long time, it genuinely was. The actual imbalance we are talking about is tiny relative to the enormous amount of energy flowing through the system in both directions, representing a difference of well under 1% between incoming and outgoing radiation at any given moment. Scientists have compared the challenge to trying to detect whether a bathtub is very slowly overflowing while enormous volumes of water are simultaneously pouring in through the faucet and draining out through the drain at almost, but not quite, the same rate. The tool that finally made this kind of precision measurement possible is a NASA satellite mission called CERES, an acronym for Clouds in the Earth's Radiant Energy System, which has been continuously operating since the year 2000. CERES instruments, carried aboard a rotating fleet of polar orbiting satellites, directly measure both the sunlight reflected back into space and the thermal infrared radiation emitted from the top of Earth's atmosphere, essentially keeping a running, planet-wide ledger of energy income and energy expenditure. Because the imbalance itself is so small, scientists also cross-check the CERES satellite readings against a completely independent measurement system, a global network of thousands of robotic floating instruments called Argo, which drift throughout the world's oceans, continuously measuring temperature at different depths. Since roughly 90% of any excess energy accumulating in the climate system ends up being absorbed by the oceans, tracking how quickly the oceans are warming provides an entirely separate way to estimate the same underlying imbalance. And when two completely independent measurement systems, one looking down from satellites in orbit and one measuring directly from within the ocean itself, arrive at strikingly similar answers, that agreement gives scientists real confidence that what they are detecting is a genuine physical phenomenon, rather than some kind of instrument error or statistical artifact. And that is precisely what happened in 2021, when a team of researchers from NASA and the National Oceanic and Atmospheric Administration published findings comparing these two independent datasets directly against each other for the first time over an extended period. What they found was striking enough to make headlines well beyond the usual scientific press. Earth's energy imbalance had roughly doubled over a 14-year stretch between 2005 and 2019, climbing from approximately 0.5 watts per square meter during the early part of that window to close to 1 full watt per square meter by the end of it. Norman Loeb, the lead author of that study and the principal investigator for the CERES mission at NASA's Langley Research Center, described the agreement between the two completely independent measurement methods as remarkably strong, giving the research team real confidence that they were looking at an authentic trend rather than some kind of measurement glitch. In his own words describing the finding, he called the trend they had uncovered quite alarming in a certain sense, a notably blunt characterization coming from a scientist whose entire career revolves around treating data with careful, measured caution rather than dramatic language. That 2021 finding alone would have been significant on its own, but the story did not stop there, and this is really where the situation shifts from a single interesting data point into something closer to an open, actively debated scientific puzzle. In 2025, an updated and expanded analysis led by climate scientist Thorsten Moritzen and published in the journal AGU Advances extended the CERES record even further and found that the trend had not leveled off or slowed down at all. If anything, it had accelerated. According to that more recent analysis, by 2023, Earth's energy imbalance had reached roughly 1.8 watts per square meter, which researchers noted was approximately twice what climate models had projected the imbalance should be at that point, given the amount of greenhouse gases humanity has added to the atmosphere. Moritzen himself, in comments accompanying the publication, was remarkably direct about how unexpected this result was, even to the scientists who study this exact subject for a living. He described the rapid rise as something that had genuinely taken the scientific community by surprise, adding that if the trend continued for even a few more years and could be confirmed through independent data, researchers would essentially find themselves operating beyond the boundaries of their current understanding of how the climate system behaves. That is an extraordinary thing for a climate scientist to say publicly about a phenomenon, this fundamental to how the entire field models the future of the planet's climate. To understand exactly what within the imbalance is driving the surprising increase, it helps to break the number down into its two component parts, because the specific direction of the surprise turns out to matter enormously for figuring out the underlying cause. Researchers analyzing the CERES data found that the overall increase in Earth's energy imbalance results from two competing effects happening simultaneously. There has been a meaningful increase in the amount of solar radiation the planet is absorbing, meaning Earth has effectively become somewhat darker and less reflective than it used to be, absorbing more incoming sunlight rather than bouncing it back into space. At the same time, there has also been an increase in the amount of outgoing long-wave radiation escaping back out to space, which on its own would tend to partially offset and cool the imbalance. But the increase in absorbed solar radiation has outpaced the increase in outgoing heat loss by a wide enough margin that the net imbalance keeps climbing anyway. This detail matters because it points scientists toward a specific category of explanation. A straightforward increase in greenhouse gas concentrations primarily affects the outgoing long-wave side of this equation, trapping more heat that would otherwise escape to space. But the dominant driver behind this particular surprise appears to be happening on the solar absorption side instead, meaning something is changing about how reflective the planet's surface and atmosphere actually are. A category of change that traces back to Earth's albedo rather than directly to greenhouse gas concentrations alone. That distinction is exactly why researchers investigating this puzzle have focused so heavily on clouds, ice, and airborne particles called aerosols, because all three of those factors directly influence how much sunlight gets reflected away before it can be absorbed. One especially compelling piece of the puzzle involves a policy, change that had nothing to do with climate science at all when it was originally enacted. In 2020, the International Maritime Organization implemented new global regulations, dramatically cutting the allowable sulfur content in the fuel burned by the world's cargo ships, a policy designed purely to reduce air pollution and improve public health in coastal regions and shipping lanes. Sulfur emissions from ship exhaust, however, had long been known to seed the formation of bright, reflective low-altitude clouds over the ocean, clouds that, while an unhealthy byproduct of pollution, were also inadvertently reflecting a meaningful amount of sunlight back into space and had been doing so for decades without most people realizing it. Removing that sulfur pollution improved air quality and public health, which is an unambiguously positive outcome, but it may have simultaneously and unintentionally removed a significant reflective effect that had been quietly masking a portion of the planet's true underlying warming trend, essentially pulling back a curtain that had been partially hiding how much energy the climate system was actually absorbing all along. Beyond the shipping regulation angle, researchers have also pointed to broader changes in cloud cover itself as a major contributor. And this is genuinely one of the more difficult pieces of the climate system for scientists to model accurately, even under normal circumstances. Clouds, particularly low-altitude clouds over the ocean, are among the brightest, most reflective features on the entire planet. And even small shifts in how much low cloud cover exists over a given ocean region can meaningfully change how much sunlight that region absorbs versus reflects. Researchers meeting to discuss this exact issue have proposed that reductions in cloud cover, potentially connected to shifting sea surface temperature patterns, changes in large-scale atmospheric circulation, or the broader decline in reflective aerosol particles discussed a moment ago, could be playing a central role in the darkening trend showing up in the satellite data. Declining sea ice and snow cover near the poles add yet another contributing factor, since both ice and snow are extremely reflective surfaces, and as they shrink in area, they expose darker ocean water and darker land underneath, each of which absorbs considerably more sunlight than the bright ice or snow that used to cover it. A separate and genuinely fascinating study published in October of last year added another layer of nuance to this entire picture by looking not just at the planet as a whole, but at how the northern and southern hemispheres are behaving differently from each other. Norman Loeb, the same researcher who led the original 2021 doubling study, worked with colleagues to analyze 24 years of CERES observations and found that the northern hemisphere has been absorbing meaningfully more solar energy than the southern hemisphere, at a rate of roughly 0.34 watts per square meter per decade faster. On its own, that number sounds small, but climate scientist John King Lee, commenting on the findings from outside the research team, pointed out that a difference this size, once scaled up across the entire hemisphere, represents an enormous quantity of additional energy. Using a specialized analytical technique called partial radiative perturbation analysis, which allows researchers to isolate how much of a given change in reflected sunlight can be attributed to specific individual factors, the research team identified three primary drivers behind the northern hemisphere's faster darkening trend: melting snow and ice reducing the region's overall reflectivity, declining air pollution, similarly, reducing the reflective haze that industrial regions had previously produced, and rising atmospheric water vapor, which itself both traps outgoing heat and interacts with cloud formation in complex ways that are still being actively studied. The finding matters well beyond simple planetary bookkeeping too, because an increasingly lopsided distribution of absorbed heat between the two hemispheres has real potential to reshape global wind patterns, shift where and how heavily rain falls across different regions, and alter the broader circulation systems that determine regional climate and weather patterns for billions of people living in both hemispheres. It also helps to understand just how long and unusually consistent this overall record actually is, because the strength of a scientific finding, like this one, depends heavily on whether it shows up reliably across an extended, continuous stretch of time, rather than in a single unusual year or two. When researchers examine the complete CERES record stretching back to the year 2000, rather than focusing on any shorter subset of it, the trend looks even more pronounced than the original headline doubling figures suggested. Along the best fit trend line calculated across the entire available record, Earth's energy imbalance climbed from somewhere around 0.34 watts per square meter, near the turn of the century, to roughly 1.4 watts per square meter. By early this year, an increase approaching a fourfold rise rather than merely a doubling, working out to an average increase of about 0.44 watts per square meter with every passing decade. Researchers examining this longer record have also specifically checked whether the trend holds steady through very different underlying climate conditions, comparing behavior during the well-known global warming slowdown that ran roughly from 2000 to 2010, the transition into a strong El Niño event between 2010 and 2016, and the years immediately following that El Niño event through 2022. Despite the surface temperature record itself looking meaningfully different across each of those three distinct periods, the underlying trend in the net top of atmosphere energy imbalance stayed remarkably consistent throughout all three, varying by less than 1/10 of a watt per square meter per decade between them. That consistency across such different short-term climate conditions is itself a meaningful piece of evidence, since it suggests researchers are looking at a genuine, steady underlying acceleration in how much energy the planet is retaining, rather than some kind of short-term statistical fluke tied to any single unusual year, any particular ocean cycle, or any one especially hot or cool season skewing the broader picture. Given just how significant and still unresolved this puzzle has become, the scientific community responded earlier this year in a way that tells you a lot about how seriously researchers are actually taking it. In March of 2026, 44 climate researchers from institutions across Asia, Europe, and North America gathered at Ringberg Castle on the shore of Lake Tegernsee in Germany, at the invitation of the Max Planck Institute for Meteorology, specifically to sit down together and work through what is actually driving this trend. This was not a routine annual conference. It was a dedicated, focused workshop convened around one specific open scientific question, which is itself a meaningful signal about how urgently the community wanted to compare notes and pool expertise on this exact topic. The published summary of that workshop's conclusions confirmed the core trend once again using the full run of CERES data available through 2024, finding that Earth's energy imbalance had increased by somewhere between 0.3 and 0.5 watts per square meter per decade across the full period from 2005 through 2024. The researchers concluded that this trend has been driven predominantly by changes in the shorter wavelength, solar reflecting side of the equation, rather than the longer wavelength heat trapping side, essentially confirming in more detail the earlier finding that the planet has genuinely become measurably darker, absorbing more sunlight than it used to, largely because of retreating polar ice and a reduction in cloud cover. Rather than settling on a single definitive explanation, though, the workshop's outcome was a set of specific, testable hypotheses that the participating researchers now plan to investigate further, including proposals for dedicated field measurement campaigns, additional satellite observations designed to isolate specific variables, and an intriguing new avenue that has only recently become computationally realistic: running full climate simulations at a kilometer-scale resolution covering the entire 24-year span of the CERES satellite record. A level of detailed simulation that would have been far beyond available computing power just a few years earlier. It is worth pausing on why kilometer-scale simulation represents such a genuine leap forward here, because the distinction between older and newer climate models is not simply a matter of running the same calculations faster. Traditional global climate models typically divide the planet's atmosphere into grid cells spanning somewhere between 50 and 100 kilometers across, a resolution coarse enough that individual clouds, which often form and dissipate over distances of just a few kilometers, cannot actually be simulated directly and instead have to be approximated using simplified mathematical shortcuts called parameterizations. Those shortcuts have long been recognized by climate scientists as one of the single largest sources of uncertainty in any climate model, precisely because clouds play such an outsized role in determining how much sunlight the planet reflects versus absorbs. A model capable of directly simulating individual cloud formations at a kilometer scale, rather than approximating their aggregate behavior across a much coarser grid, offers researchers a genuinely new way to test whether existing cloud-related assumptions are actually responsible for the gap between predicted and observed energy imbalance. Running a simulation at that resolution across the entire multi-decade CERES record requires an amount of computing power that simply did not exist in any research institution as recently as 5 or 6 years ago, which is part of why this specific avenue of investigation is only becoming possible right now, rather than having already been tried and ruled out years earlier. It is worth being genuinely careful and precise here about what this growing body of research does and does not actually establish. Because a story like this one gets pulled in two very different, equally misleading directions the moment it starts circulating more widely online. On one side, it is tempting to frame an unexpectedly large Earth energy imbalance reading as proof that warming is now spiraling wildly out of control in some kind of sudden, catastrophic new phase that existing science completely failed to anticipate. That framing overstates what the data actually shows. The fundamental direction of the trend, a warming planet absorbing more energy than it releases, remains exactly what climate science has predicted and understood for decades, confirmed here by two entirely independent measurement systems agreeing closely with each other. What is genuinely uncertain and being actively debated is not whether the planet is warming, but specifically why the pace of energy accumulation has outrun the rate that existing climate models projected, and by how much that pace might continue accelerating going forward. On the other side, some commentators skeptical of mainstream climate science have seized on this exact same body of research to argue that since models failed to predict the size of this trend accurately, the entire field of climate modeling must be fundamentally unreliable or not to be trusted at all. That framing gets the actual scientific process backwards. Scientists identifying a real discrepancy between model predictions and precise satellite observations, then organizing a dedicated international research effort to figure out exactly why that discrepancy exists. Is the scientific method functioning exactly as it is supposed to? Refining and improving understanding by confronting predictions directly with new, higher quality data, rather than evidence that the underlying science was wrong from the start. Climate researcher Thorsten Mauritsen's own comments make this distinction clear. His concern was never that the planet's warming direction had somehow been disproven. His concern was that the rate of change was moving faster than current models could adequately explain, and that figuring out precisely why matters enormously for making accurate projections about the decades immediately ahead of us. There is also a genuinely separate and more immediately practical concern connected to this entire story. one that has less to do with interpreting the data itself and considerably more to do with whether scientists will even be able to keep collecting data of this quality going forward. The CERES satellite instruments currently providing this critical measurement capability were never designed to operate indefinitely, and several of the satellites carrying them, including the long-running Terra and Aqua missions, are now well past their originally planned operational lifespans and are increasingly experiencing fuel and power limitations as they continue operating years beyond their intended retirement. A planned successor mission called Libra is currently scheduled to begin flying in the coming years to continue this exact measurement record, but researchers involved in this area of study have raised a specific, pointed concern about that transition. Unlike the current CERES program, which benefits from having multiple overlapping satellites providing redundancy and continuous cross-validation against each other, the initial Libra mission is planned to launch with only a single satellite. Scientists interviewed about this transition risk have warned that a single instrument failure during that critical handoff period could introduce troubling gaps in an otherwise unbroken, more than 2-decade-long continuous data record, right at the exact moment when understanding whether this energy imbalance trend is continuing to accelerate, stabilizing, or beginning to reverse matters more than at almost any previous point in the history of the measurement. One scientist studying this exact risk was quoted describing the potential consequence of losing continuous measurement capability during this uncertain period in particularly stark terms, warning that without it, the research community risks being effectively blindfolded to the true severity and trajectory of ongoing climate change at precisely the moment that clarity matters most. Stepping back from the individual technical details for a moment, it is worth thinking through why a single abstract number like this one carries so much practical weight for how climate science actually gets used by policymakers, businesses, and governments planning for the decades ahead. Surface temperature records, the kind of statistic most people are familiar with from annual headlines about record-breaking hot years, are influenced by a considerable amount of short-term natural variability, including phenomena like El Niño and La Niña cycles in the Pacific Ocean, which can temporarily push global average temperatures up or down from one year to the next in ways that have relatively little to do with the underlying long-term warming trend. Earth's energy imbalance, precisely because it is measured directly at the literal top of the atmosphere using consistent satellite instrumentation, offers researchers a comparatively cleaner, more direct window into the fundamental physical process actually driving long-term climate change, largely stripped of much of that shorter-term noise. Because of that directness, some researchers argue that tracking changes in the energy imbalance itself could eventually provide an earlier, more reliable warning signal for shifts in the pace of global warming than waiting years for those changes to fully show up in surface temperature statistics, which tend to respond somewhat more slowly and with more year-to-year variability layered on top of the underlying trend. That is precisely why the scientists gathered at Ringberg Castle framed continued, high-quality monitoring of this specific number as such an urgent priority, arguing that closely tracking the energy imbalance in the years ahead could provide one of the very earliest, most direct indications of whether global efforts to reduce greenhouse gas emissions are actually beginning to show up as a measurable slowing in the rate at which the planet is accumulating excess heat, likely appearing in the specific data stream years, or even decades, before the same signal would become clearly visible in surface temperature records alone. This is also part of why the specific magnitude of the imbalance matters so much to anyone trying to plan for future climate impacts rather than simply describing past ones. Researchers have occasionally used rough comparisons to communicate just how much energy a number expressed in fractions of a watt per square meter actually represents once it is scaled up across the entire surface area of the planet, and even a seemingly modest doubling or near quadrupling of that number carries outsized practical significance for future sea level rise, ice sheet stability, ocean heat content, and the frequency of extreme heat events, since each of those downstream consequences is ultimately being driven by exactly this underlying energy, surplus continuing to build year after year. All of this leaves us with a genuinely open scientific question, rather than a fully settled conclusion. And being honest about that distinction is really the whole point of understanding this story properly, rather than just reacting to the most dramatic possible headline describing it. Multiple independent lines of evidence, satellite-based radiation measurements, ocean heat content data gathered from an entirely separate global network of floating sensors, and detailed hemisphere-by-hemisphere analysis of exactly where and why the planet is absorbing more sunlight than it used to, all consistently point toward the same underlying conclusion. Earth is accumulating energy at a pace that has clearly outrun what existing climate models predicted just a decade or two ago, and the primary driver behind that, unexpected acceleration, appears to be a genuine decline in the planet's overall reflectivity, likely arising from some combination of retreating polar ice, reduced cloud cover, and the mostly beneficial but seemingly consequential reduction of sulfur pollution from global shipping. What remains considerably less certain is exactly how much weight to assign each of these individual contributing factors relative to one another, whether the trend itself will continue accelerating, level off, or eventually reverse course in the years ahead, and precisely what all of this implies for the pace of future warming projected over the remainder of this century. Those are exactly the kinds of specific, testable questions that the researchers who gathered together this year at Ringberg Castle are now actively working to answer through a combination of new field measurement campaigns, additional dedicated satellite observations, and increasingly detailed computer simulations that have only recently become computationally feasible to run. What makes this story genuinely worth paying close attention to, beyond the raw scientific intrigue of it, is what it reveals about how climate science as a discipline actually responds when its own most careful predictions turn out to be measurably wrong in some specific, quantifiable way. The instinct in a moment like this is not to quietly bury an inconvenient discrepancy, nor is it to declare the entire body of climate science fundamentally broken because one particular projection undershot what the real world subsequently delivered. The instinct, and the actual response happening in real time across research institutions on 3 separate continents right now, is to treat an unexpected reading as a genuine invitation for deeper investigation, converging researchers, funding, and increasingly sophisticated tools directly onto the specific gap between prediction and observation, until they can explain precisely why that gap exists and what it means going forward. That process is still actively unfolding as this video is being made, with new field campaigns being planned, new satellite missions racing against the retirement of the aging instruments currently doing this critical work, and new high-resolution simulations beginning to run using computing power that simply did not exist when the original CERES mission first launched back in the year 2000. If this kind of deep, evidence-based breakdown of the science behind a genuinely open scientific question is useful to you, subscribing means you will not miss the next update as researchers continue working through exactly what is driving this trend, and sharing it with someone who has heard climate models described as either infallible or completely unreliable is a genuinely useful way to spend the next 30 seconds, since the real, more interesting truth sits somewhere considerably more nuanced than either extreme. Let me know in the comments whether a story like this, about scientists openly rechecking their own models rather than simply defending them, changes how much trust you place in the broader body of climate research, and whether you had ever heard of Earth's energy imbalance before today, because it remains one of the most important numbers in all of climate science that almost nobody outside the field has ever actually heard of. Either way, roughly 700 kilometers above your head right now, a small fleet of aging satellites is still quietly keeping score on exactly how much extra energy this planet is holding on to, and the number they keep reporting back is one that an entire international community of scientists is still working hard to fully explain.